So, hello, what's up, guys? Today we are going to solve even Fibonacci number, question number 2 from the Euler project. So, what is the Fibonacci number? Let's see. Fibonacci number is like, let's say we have been given two numbers, 1 and 2. Then Fibonacci will be nothing but just the sum of the just last two numbers. Like for 1, 2, we will going to have 3. And for this sequence, we are going to have 3 plus 2 is 5. And then 3 plus 5 is 8 and so on. So, this is basically Fibonacci numbers. So, the question is saying we need to find let's say we have given some input 10. So the Fibonacci number in till 10 is going to be what? 1, 2, 3, 5, 8. After this, we are going to have 13, and 13 is outside the 10. So we need to find sum of the even numbers which is below the our input number in the Fibonacci series. This we need to find. So for the 10, our output is going to be, let's see, there are two even number which is below 10 and their sum is 10. So for the 10, our output is going to be 10 only. Now let's say one more input is there in our test case, in our example test case, that is 100. So if you see, after 13 we are going to have 21, and then we are going to have 34, and then we are going to have 55 and 89. And if you are going to see the even numbers are 34, okay, 8 and 2. So we are going to have 44. So this is what question wants from us. Now let's solve. So there is nothing much in this question. What we can do is we will simply take two numbers inside our array. Let it be 1 and 2. And what we are going to say that first thing is that Fibonacci numbers are very fast increasing. Means they are increasing very fast. Even though our input is how much? 4 into 10 to the power 16. This is the range of our input. But the thing is, our Fibonacci number is going to increase very fast, very fast. So if it is going to increase very fast, till you can assume that maximum is going to be 100. In 100 in only 100 loop we are going to reach 4 into 10 to the power 16, nearly equal to 4 into 10 to the power 16, or more than 4 into 10 to the power 16, we don't know. So I said we are going to have a loop till 100, and we are going to just sum up, like 1, 2 will become 3, 5, 8. We are just summing the last two numbers. 3 plus 5 is 8, and 8, and again we are going to have 13, and like this we are going to have 21, 34, 55. You can see how fast the number is increasing, and the more you go ahead, the number is going to be increasing very rapid. Soon, in just 44 or 45 cases, you are going to have 10 to the power 14 or 10 to the power 12, like these very large numbers. So we can say that in only 100 steps, we are going to just calculate the brute force way for the Fibonacci number. We are going to calculate the Fibonacci number in the brute force way. And as soon as our n is matched, we are going to say, hey, we need to stop. And in between, while traversing from 1 to 100, if at the moment when we are going to see that our current element is even, we are going to simply add that number in our sum. Let's dry run our code, whatever we are thinking. Let's say input number was 100, okay, and I said we are going to traverse to 1 to 100. So for the first and our pre-built arrays, what 1 and 2 is already present in our array, okay. So now I know my sum will always start from 2, since our array, since we need to find even numbers, and we have already put one even number in our array. Now when I is 1, when we are 1, we are going to simply sum up these 2, and we are going to have 3, and simply I will become 2. Then it is going to have 5, 8, 13. See, 8 comes, so I'm going to add that into sum also. 13. Then we are going to have 21, 34. Yeah, 34 is even, so I'm going to add 34, and like this. Whenever it's go beyond the our input number, which is 100, after 89 it is going to be exceeded. So since 89 plus 55 is greater than 100, we are going to break, and we are going to simply say, hey, 44 is our answer. So this is what we are thinking. But the fantastic thing about this question is that we don't need to go 1 to 100. Okay, yes, you can go 1 to 100, and eventually one time will be there that we are going to stop. But can we calculate our this exactness of exactness where our loop is going to end? Like, we are not going to want random. We don't want random. We just want the exact place where our eye is going to stop. Or why we are just taking 100? How you are just so much confident that after 100 our Fibonacci sequence is going to be end? Let's see. See, there is one formula which is given by Binet's formula. We call it as a Binet's formula. Let me write it down. It's a Binet's formula. So what the Binet's formula says, let's say, it says that you can calculate Fn. Fn is your basically nth term of your Fibonacci number. You can calculate it using 5 to the power n minus psi to the power n by root 5. So it's using this formula. You can see derivation of this formula on internet. I'm not going to derive it. So using this formula, we can easily calculate basically the Fibonacci number, nth Fibonacci number. If you want to get fifth Fibonacci number, sixth Fibonacci number, like already I said, 1, 2 is there, like 3, 1 plus 2 is 3, now 2 plus 3 is 5, 5 plus 3 is 8. You can directly calculate 8. You don't need to do this thing like summing the last two. So using this, you can calculate easily. Now, what is phi n and what is psi to the power? Phi to the power n, what is psi to the power n? So phi to the power n is called the golden ratio. And yeah, golden ratio, you must have heard it. The value of the golden ratio is 1 to the 1 plus root 5 by 2. This is called the golden ratio. Yeah. And psi value is going to be nothing but 1 minus root 5 by 2. Yeah. This is the value of phi and this is the value of psi. Now, since you can see if n will be very large, we can ignore psi to the power n and we can only take phi to the power n. Okay. And we can say that fn is going to be what? Phi to the power n. Can I say by it is going to be by root 5? Yeah, sure. Now we need to find the value of n, how we can get the n. So let's see how we can get the n. Now we have phi to the power n minus psi to the power n by root 5. So, and we know the value of phi to the power n is what? 1 plus root 5 by 2. And we can say that its value is nearly equal to, if you are going to calculate it, is going to be 1.618. Easily it is going to be 1.618. So we have this 1.618 from the value of phi to the power n. Now let's see what we can do. Can I say that we are going to take log both sides? So I said I'm going to take 1 second. Yeah, just I'm going to take log both sides here. So I said ln f of n is going to be equal to ln phi to the power n by root 5. Can I say that? Using the logarithmic formula, can I say that ln phi to the power n minus ln of root 5 is equal to ln of fn? Yeah. Now can I say that? Can I pull out n outside? Yeah, sure. So I said n of ln is log basically, phi minus half of log of phi. Can I say that? Yeah, surely. Now we can use this n to calculate whatever we were interested to find. Now can I say that n is going to be what? N is going to be ln of fn plus half of ln f by, we are going to simply put value of our golden ratio, which is what we calculated earlier, 1.618. So this is what n is. And in our input it is saying that we need to calculate how much we need to, our max n can be 1 e to the power 14. I think it is 1 e to the, let me check, let me confirm. No, it is saying 1 e to the power 16, 4 into 1 into 1 e to the power 16. So this is going to be our max input value. So if this is the max input value, then how much iteration we need to do? Let's see. So I said ln of 4 times 1 e to the power 16, okay, plus half of ln of 5 by ln of 1.61. Can I say that? Yeah, surely. Okay. Now can I say that this value is how much? This value is nearly equal to 48. If you will calculate 4 into 1 e to the power 16, this value is nothing but 48. And you can say that plus 0.8, this value, half of ln of 5 is have value of 0.8. And can I say that ln of 1.618 is nothing but 0.418. And if we are going to calculate, we are going to get nearly equal to 78. 78 or basically no, 81. We are going to get 81. Yeah. 81 is going to be answer. So using this Binet's formula, we came to know that after 81 iteration, we are going to reach nearly equal to how much? 4 into 1 into the power 16. And this is what we are interested in. So if you see my code, let me show you my code. Yeah. If you see, I have taken my sum as 2 since we have a by default even value in our array. That is 2. So I have taken a by default value of sum is equal to 2. Now if you see, I have taken n as 100. Okay, I have taken n as 100. And sorry, I've taken total number of iteration as 100. You can see I am saying that max number of iteration I'm going to do is 100. So after each iteration, we are just adding last two values of our vector, vec plus 1, and we are just checking if my current value, the last value of my vector, is greater than n, then we are simply breaking it. But if it is not, then we are checking whether it is the divisible by 2 or not. If it is divisible by 2, we are simply adding in our sum, and we are just returning our sum. We are just saying whatever the sum value is, and we are just returning. So if you will see, let me show you, this is our code. If you see, uh, see here I am taking 78 value. Why? Our whatever value we calculated, you must have seen it given us 80, approx 80, nearly equal to 80. So it is saying that after 80 we are going to, till 80 we are not going to cross 4 into 10 to the power 16. So it is saying nearly equal to. So if you will take any number below the 78, I checked it, that below the 78, then it is not going to work. See, if I'm going to take 77, it is not going to work. See, test case 3 failed. But we have already proved that a number which is nearly equal to 80, we are going to surely get the right answer. So if you take I as smaller than 80, it is going to work like crazy. Yeah, it's working.